Hi, and welcome to the section 2.5 lecture video. This time we're going to be building on the idea of limits that we've been looking at so far in this class and talk about an idea called continuity. So if you want to go ahead and take out a copy of your chapter 2 note sheets or just some paper to take notes on, that's fine. Go ahead and do that now. If you're looking for a copy of the chapter 2 note sheets, remember these can either be found on your Blackboard course if if you're taking this course online, or if this is a hybrid or in-person class, you can also find these under handouts in my math lab. Okay, so we're going to get started here on section 2.5. So continuity. So let C be a real number that is either an interior point or an endpoint of an interval in the domain of f. The function f is continuous if the limit as f of x as x approaches c of f of x is equal to the function value at c. Okay, so we've seen with these limits we've been doing a lot of the times that the limit is not the same as the function value. So in those cases, the function would not be continuous. But if the limit is the same as the function value, then at that point, the function is continuous. The function is said to be right side or right hand continuous if the limit as x approaches c from the right of f of x equals f of c, and the function is said to be left side continuous or left hand, or another way to say this would be continuous from the left if the left hand limit, the limit as x approaches c from the left, is equal to the function value. We say that a function is continuous on the interval a comma b if it is right hand continuous at a, left hand continuous at b, and continuous at all interior points of the interval. This definition holds for infinite closed intervals and as well. So the continuity test. So there are three things that have to happen to be continuous. So a function f of x is continuous at a point x equals c if and only if it meets the following three criteria. First of all, a has to be less than or equal to c, which is less than or equal to b. So that means c lies in the domain of f. F has to have a limit. So the limit as x approaches c of f of x exists. Actually, I wrote the wrong thing here. It occurs to me now that I've done that one. This first one should say f of c exists. And the limit equals the function value. So what we have up here. So the limit as x approaches c of f of x has to equal f of c. Okay, so here are some graphical representations of ones that are continuous or not continuous. So what you should notice here is if we look at 0, the only one of these that is continuous on both sides is this first one. So this first one is continuous on both sides. Notice here, there is no function value, so this breaks rule 1 because there is no function value there. Here, this breaks rule 3 because the function value is 2, but the limit is 1, so they're not equal to each other. This one doesn't have a limit at c, right? Because it comes from two different directions. But this one would be right continuous. Because on the right-hand side, the limit as x approaches 0 from the right of f of x equals 1, which is equal to f of 0. So that one would be right side continuous, but it's not continuous in general. The other two down here at the bottom, these are both not continuous because there is no limit at either one of these. So these break rule 2. There is no limit there. So those are not continuous there either. We define a continuous function to be one that is continuous at every point in its domain. If a function is discontinuous at one or more points, we say it is a discontinuous function. So one of the nice things about properties of continuous functions is they break down really nicely into smaller and smaller pieces. So for example, it says if the function f and g are continuous at x equals c, then the following algebraic combinations are continuous as well. F plus g is continuous, f minus g is continuous, a constant multiple k times f is continuous, f times g is continuous, f divided by g is continuous, as long as g of c does not equal 0. F to the nth power is continuous, and the nth root of f is continuous. Assuming that n, for this last one, f of c is greater than or equal to 0 when n is even. So the two caveats here are just to make sure that the combination doesn't become undefined, right? We can't divide by 0, so that's why number 5 has this caveat, and we can't take the square root or the fourth root or the sixth root, an even root of a negative number. So that's why we have this caveat for number 7. Okay, and then also one more thing with composition of functions. So if we combine functions together, if f is continuous at c and g is continuous at f of c, then g of f of c is continuous at c. And this would be true the other way around too. So composition also works this way. So what this allows us to do is it allows us to ask ourselves, well, to break these things down and see if there's anywhere they would not be continuous. And then compare that to look at these caveats is where we're mostly going to run into an issue. So like, for example, here, this is a linear function, and this on the bottom is a quadratic function. Those are both going to be continuous functions. There aren't any gaps in functions that look like that. So that means this thing should be continuous everywhere except when we run into this caveat for division, except when the denominator is equal to 0. So what we want to do is we want to say, well, what happens when the denominator is equal to 0? And then solve that, and that'll tell us where this thing is discontinuous, and so everywhere else it'll be continuous. So we can factor this. Two numbers that multiply to get negative 10 and add to get negative 3 are negative 5 and positive 2. And so we end up with x equals 5 and x equals negative 2. So the function is discontinuous at these points. So it's continuous everywhere else. And so the way we can write that is with interval notation. This would be continuous from negative 5 to negative 2, from negative 2 to 5, and from 5 to infinity. So we go from negative infinity to infinity, but we hop over negative 2 and we hop over 5, because those are the places where it's discontinuous. Okay. So the same kind of idea goes for the next one, right? So if this top thing is definitely linear, so that's definitely continuous, and the cosine function is also continuous. We could graph it if we wanted to check that, but there's no jumps in the cosine function. So once again, the question is just when is the denominator equal to 0? Okay. And so we know the denominator to be equal to 0. And you can check this with a graphing calculator. But if you remember back to trig, we know the denominator to be equal to 0 at pi degrees. At pi over 2 degrees, 3 pi over 2 degrees, and so on. And so the way we can write that is this thing is going to be discontinuous at all x that are equal to pi over 2 plus some constant times pi, right? Because they're 180 degrees apart, but they start at 90 degrees. So it would be 90 degrees plus, which is pi over 2, plus pi is 3 pi over 2, plus pi is 5 pi over 2, plus, and so on. And also the other way, pi over 2 minus pi is negative pi over 2. So that's how we would say where it's discontinuous. So we could say it's continuous at all x such that x does not equal those values. So we could use some set builder notation to write where that one is discontinuous. Okay. And then if we look at the third one here, this one, the function in here, we know that if the composition function is continuous as long as the pieces are continuous, so the inside's fine, that's continuous. We also have this root rule that tells us that this thing should be continuous as long as the inside isn't negative when the root is even. Well, in this case, the root's even, so that means we need to know when is 3x minus 1 greater than or equal to 0, and that's where our function will be continuous. So we're going to add 1 to both sides and then divide by 3. So x is greater than or equal to 1/3. Okay? And so we can write that in interval notation as 1/3 to infinity. Okay, and so that's the idea. So what I'd like you to do is go ahead and take a few moments, pause the video here, and see if you can figure out these problems. Okay, now that you've given these a try, let's go ahead and go through them together. So for the first one, the only thing that's a problem is this denominator can't be 0. So let's check and see if there's a time when that's 0. Okay, so square root both sides, subtract 2, and so we get x equals -2. So that's when the function is discontinuous, so it's continuous everywhere else. Okay, this one, cosecant of 2x, well, that's just y equals 1 over sine of 2x, and so we can solve. So we want, in this case, the problem is, well, the denominator can't be 0. So we set the denominator equal to 0, and we can solve. So that's 2x. Now, when is sine equal to 0? Well, sine is equal to 0 at 0, and at pi, and at 2 pi, and at 3 pi, and at negative pi. So that's at k pi. And then we can simply divide both sides by 2. So this would be x equals k pi over 2. Is when that would be equal to 0. And so what we can say is this is continuous at all x's except when x does not equal k pi over 2. Okay, so that's that one. This one, we have an even root again, right? Because this is a square root because there is no number, so the root's 2. So we set the denominator, not the denominator, the radicand, the thing inside the radical, greater than or equal to 0. And solve for x. Okay, and so this time -3/2 to infinity is where this function is continuous. Now with this next one, we can start out, we want to look at this piece, okay? So here the problem appears because it's a piecewise function that this is going to happen at where this piecewise breaks up. So if we look at this function, we know that this top part is undefined and therefore discontinuous at 3. But the question is, what if we plug in the value 5 there? So what's the limit of this thing? is what we care about. So what we need to do is we need to try and find the limit as x approaches 3 of x squared minus x minus 6 over x minus 3. Because remember, functions are only discontinuous if the limit doesn't equal the function value. So far, all the ones we've looked at, what we've actually run into is there is no function value at these places. And so that's why these have been discontinuous. This one, though, there is no function value for this top piece, but there might be. If this function value 5 matches up with what this limit is, then we'll be fine. This won't be discontinuous anywhere. So the limit as x approaches 3, and then we factor the top. So two numbers that multiply to get negative 6 and add to get negative 1 are x minus 3 and x plus 2. And we can cancel the x minus 3's, and now we can just plug in 3 for x. So this limit will equal 3 plus 2, which is 5. And so now the limit is equal to the function value, so this is continuous everywhere. There is nowhere that this is discontinuous. By adding this piece that x, when x equals 3, the function is 5, they fixed where this would have been discontinuous. This idea of continuity can also help us with finding some limits by using the limits of continuous functions theorem. So if the limit as x approaches c of f of x equals b, and g is continuous at the point, and this should say c, not b, c, then the limit x as approaches c of g of f of x is simply g of b. So what this allows us to do is, if we're finding a limit like this where we have a composition of functions, a function within a function, we can simply find and put the limit inside the outside function, assuming the outside function is continuous at that point. And one really easy way to check is just to try it. Okay. So assuming this function isn't undefined at 1, we can go ahead and try it out. So let's see what happens. So if we just plug in 1, so this would be 1 times secant squared of 1 minus tangent squared of 1 minus 1. Okay, and so that's secant of secant squared of 1 minus tangent squared of 1 minus 1. And this is actually one of our trig identities. Specifically, that's secant squared theta minus tangent squared theta equals 1. So this is secant of 1 minus 1, which is secant of 0. And if you plug that in a calculator, if you just remember, your trig value secant of 0 is simply 1. Okay, so that's simply how that works. So similar idea with this one, right? I can use my limit rules to break this apart into two limits, right? One of the limit rules says that quotients, you can simply plug in okay, and now we can really just use our limit rules, right? So this is just going to be pi over the square root of 19 minus 3 secant of 2 times 0, which is pi over 19 minus 3 times 1, which is pi over the square root of 16, which is pi over 4. Okay, and so the same idea would work for this last one. So if you want to pause the video for a moment and try this last one first, you can. But otherwise, we're just going to go through it right now. So this would be sine of the limit as x approaches pi of x minus sine x. So that's sine of pi minus sine of pi, which is sine of pi minus 0, which is sine of pi, which is 0. Okay, and so that's the idea. So one of the other things we'd like to be able to do is we'd like to be able to make a function continuous and figure out when a function needs to be continuous. So in this example, the first example, it says define f of 1 in a way that extends f of s equals the s cubed minus 1 over s squared minus 1 to be continuous at x equals 1. Well, the problem right now, right, is that f of 1 is currently undefined. Or f of 1 does not exist. Right? If I plug in 1 into this function, I get 0 on the denominator, and that's undefined. And so that's a problem. So we can try and fix that. And the way we fix that is by making f of 1 equal to the limit, right? A function is continuous. So continuous if the limit as s approaches 1 of f of s equals f of 1. So what we want to figure out is, well, what is the limit at 1? And then we want to make f of 1 be that. So that's what we're going to start out with. So we want to find the limit as s approaches 1 of s cubed minus 1 over s squared minus 1. Okay, and to figure that out, we can factor. So the top factors is s minus 1 times s squared minus plus s plus 1. And the denominator factors as s minus 1 times s plus 1. Right, that's the difference of cubes on top is how we factored that, and difference of squares on the bottom. That's how we factored that. Cancel out the common denominators, and so we get the limit as s approaches 1 of s squared plus s plus 1 over s plus 1. And now I can just plug in 1. So this will be 1 squared plus 1 over 1 plus 1, which equals 3 halves. So that's the limit. And so for it to be continuous, that's what we want f of 1 to be. So let f of 1 equal 3 halves. And then the function would be continuous. Okay? Similar idea here. What I want to have happen is I have different pieces to this function. And so in order for this function to be continuous, there can't be a jump. Okay? What I need these two pieces to match up. So basically what I have on this bottom piece, right, is at 2. For anything less than that, I have the function is equal to 12. So I have a line like that. So what I need is this top piece that's going to be over here to touch that. I don't know what it looks like. I don't really care. I just need it to fill in this hole and go from there. So all we simply have to do is let a squared x minus 2a equal 12 and solve that. So we can solve that by setting one side, and we want it to happen at 2, right? So I can plug in 2 for x, and I'm setting that equal to the other piece, right? So this would be 2. Okay, so that's 2a squared minus 2a minus 12 equals 0. You can get rid of a 2 from everything by dividing everything by 2. And now we can factor. So that's a minus 3 times a plus 2 equals 0. And so then that would be a equals 3 or a equals negative 2. And either one of those values would make this work. So it could either be 9x minus 6, or it could be 4x plus 8 if I plug those values into here. Okay, but these are the values of a that would make it work. Similar idea here, except in this case I've got 2 parts. Okay, over here at negative 1, I get this function. Right, I get a line negative. Whoops, sorry, I didn't graph that right. Okay, so at negative 1, we get negative 2. And then at positive 1, we're getting 3. And so what we need to do is we need to figure out, well, what line connects those so that this whole function is continuous. Okay, so to do that, you just want to let a times negative 1 minus b equal negative 2. So you want this to equal negative 2 at negative 1. And then you also want to let a times 1 minus b equal 3. So at 1, at x equals 1, I want it to equal 3. And then we just solve this system. So this would be the opposite of a minus b equals negative 2. This would be a minus b equals 3. I can use elimination to solve this, so add these two together. So those cancel. Sorry, my 3 looked really ugly there. So it's negative 2b equals 1 divided by negative 2. So b is negative 1/2. And now I just plug that back into one of these. So a minus negative 1/2 equals 3. So a plus 1/2 equals 3. So a equals 5/2. And so there's our a and b. Okay, so why don't y'all flip to this page, pause the video for a moment, and go ahead and try these two. So the first one is similar to the first one on the previous page, and the second one is similar to the last two we just did, but slightly more challenging. Okay, so now that you've had a chance to try these, let's go and work through them together. So for the first one, I need to find the limit as x approaches 3 of x squared minus 9 over x minus 3, right? Because that's what I want g of 3 to equal. Because right now, if I plug in 3, I get 0 on the denominator, and that's undefined. So we need to define it. So this would be the limit as x approaches 3 of x minus 3 times x plus 3 over x minus 3. Cancel out the x minus 3's, and now I can just plug 3 in. So this would be 3 plus 3 equals 6. So g of 3 has to equal 6. And then down for this one, these two just need to be equal at 3 when x is 3. So that would be 3 squared minus 1 equals 2a times 3. And then we solve. So this would be 9 minus 1 equals 6a. So 8 equals 6a, divide by 6, and a equals 4/3. Okay, and that's all there is to that. Okay, and then the last thing in this section is the intermediate value theorem. So the intermediate value theorem says that if f is a continuous function on a closed interval a comma b, and if y naught is any value between f of a and f of b, then y naught equals f of c for some c in a comma b. So the idea here is, if I have a function, let's just draw a picture down here. So if I add a function that goes from a to b, and here is my f of a, and here is my f of b, any y value in between these, so any y value I pick in between those, has some c value that gives f of c equals that y naught, whatever that is, any value. So in order to go from a to b, if it doesn't have any gaps, to get from f of a to f of b, you have to go through every y value in between. A function is said to have the intermediate value theorem if whenever it takes on two values, it also takes on all the values in between. The intermediate value theorem implies that a graph of a function that is continuous on an interval cannot have any breaks over that interval. It will be continuous. So what this can allow us to do is it can allow us to find how many roots there must be. So let's define a root. So we call the solution of the equation f of x equals 0 a root of the equation, or a 0 of the function f. The intermediate value theorem tells us that if f is continuous, then any interval on f changes sign contains a 0 of the function. Okay, so for example, if I were to look at this value, we can show that the function has 3 solutions on that interval. Well, the way we do that is by finding times that it changes sign. Okay, so for example, I could graph this to get a better look at it. So if I graph, x cubed minus, so graph the function x cubed minus 15x plus 1, I believe it was. Yeah. We can see obviously where those zeros are, But you can also see that it has to have 3 of those. So like over here at -4, so we can kind of see where they are, but I can prove with the intermediate value that those 3 exist. So if I start, like I could try f of -4, based on the values we kind of look at, we could find f of -2, f of +2, and f of 4. Okay, so if I plug those values in, that'd be -4 cubed minus 15 times -4 plus 1. -2 cubed minus 15 times -2 plus 1. 2 cubed minus 15 times 2 plus 1 equal, and finally 4 cubed minus 15 times 4 plus 1. Okay, so -4 cubed is 64. -64. Plus 60 is -4. Plus 1 is -3. -2 cubed is -8. -8. And then plus 30 would be 22. So that'd be 23. 8 cubed minus 30 is -22. Plus 1 is -21. And 4 cubed is 64. Minus 60 is 4. Plus 1 is 5. So notice here, we go from a negative to a positive, so that means there has to be a 0 in here, in between. There has to be a 0 on the interval from -4 to -2, because we go from negative to positive, and so we have to hit every y value between -3 and 23, and 0 is one of those. Here we go from positive to negative, so that gives me from -2 to 2. There's 1, because we cross the x-axis again, and last but not least, this interval also has to have a 0, because once again we go from negative to positive, so that means we have to hit the y value 0, and that's the idea. So you can use the same idea to show that any value of y works. So like if f of x equals x cubed minus 8x plus 10, show that there are values of c for which f of c equals pi, square root of 3, and 5 million. Okay, so for example, we could start out, if I just graph this, so x cubed minus 8x plus 10. Okay, so for example, if I wanted to start with -√3, here's a point where the value of the function is 0. If I zoom out a little, if I go down here, let's try. Down here, I know -√3 is less than, is between 0 and -5. So here's a y value where the y value is around -5. So that means there has to be a point in here that has -√3. And the same thing would work for pi or 5 million. So that's the idea. And you could plug in values for x to show that that works. But we're not going to do that right now just to save time, because this video is long enough already. So that's the idea for section 2.5. Thank you for watching this video. Make sure you're doing your homework assignments. And don't forget, if you have any questions, you can contact me via email or through Remind.